Welcome back, guys. This is Nithish from Codezilla community, and today we'll be talking about part two of deep learning. A few weeks back, I made a part one and introduction to deep learning, and we did see a lot of good response and few deep learning enthusiasts. And today we'll be learning about uh, about the next loss functions and gradients and etc. and more complex neural networks, like I said. And let's just recap a little bit. We learned about perceptron, which is a single neuron, and a simple neural network. We had an example as well with the pass or fail, and then we were able to find the loss. And then we stopped at how to find the loss functions and loss determinations. We stopped right there. And we discussed a few activation functions, mainly three of those. So let's get into our loss functions. And the first one is empirical loss. From the last slide, last video, we could see that quantifying loss, we just found a small prediction loss, but like it was, we are supposed to get 1%, but we got 10%. So we said that this is how, I explained that this is how that the small loss can be determined, and we have to train the model. And right now we'll see this empirical loss is the total loss over the entire data set, which means you have multiple outputs. Here we just took one output. You have multiple outputs in 2 dimension, and then you get an output of the functions, just a single output basically. And then that's the thing. So it's also known as object function, cost function, empirical grids, which is JFW. This is the mathematical part. You don't need to know it. There's a TensorFlow equivalent command for it. This is the first loss function to determine a loss. And then cross entropy, binary cross entropy loss. Cross entropy loss measures the performance of classification model. It's a classification model. It's like the name suggests, it's classifying. Let's say if you're a male female, it classifies you, the data classifies you as male, the data classifies you as female. So in just numbers, it's just going to be classifying as above 5 or below 5, any criteria that we want. But right now, it measures the performance of a classification model whose output probably is between 0 and 1. So it can be 0.1, 0.2, which is like 80%-ish in our normal terms, but it's going to be within 0 and 1. This is most preferred for classification. Such kind of classification problems, this is required, where it does not require you to find the actual, let's say, the numeric prediction, numeric defined prediction. It doesn't care. It's going to classify you positive, negative, and then how much positive, how much negative. And the bottom loss determination through this TensorFlow command, the below. It's available in TensorFlow. You can, when we work on it, we'll be working on it pretty soon, and then you can definitely see how it works, how the command works basically. Mean squared loss is again another loss function, can be used on regression models. The output contains real numbers. Regression models obviously have real numbers. They cannot be between 0 and 1 because we know real numbers extend from positive to negative and then have multiple binary and decimal values. So mean square is one of the best choices for regression, but not classification, because here you get an accurate numeric value. You don't need to classify them whether they are like above 5 or below 5. I'm just giving an example. It doesn't have to be a set the classifying factor. It can directly give you a numeric final plausible value. This directly comes from the statement problem. So when we get in a question about you want to predict the weather today, it accurately predicts the temperature 36.5 degrees Celsius. How do we know it? Through passing on the regression model. And then this is to identify loss. So we are not going to talk about activation. This is how the error data. So every day the weather isn't going to be the same. So we get an error data, and that loss domain command is down below. Okay. So training and gradient descent. So in the last video, we discussed that to avoid such losses, we need more data and we need to train it better. And gradient and descent. So what's gradient and descent? So can you see the black plus marked over there? Let's say that's a gradient. Gradient in the sense that this entire 3D model graph, a gradient means like a mountain or a small hill, it grades up, a gradient, the uppermost value. So in our case, W comma W1 randomly picked. So this is going to be our gradient, which is going to be our fixed point. So to compute gradients, basically finding a slope, d of x comma d of y. That's it. Here we have dou j of function w and dou j, because jw function is our going to be our loss calculating function. So that's the reason we are finding slope of that loss calculating function and w naught. Look at the vertices, j of w0 comma w2. So yeah, so right, that's the reason here. Gradient. So it, from that point it goes to the maxima, the local maxima value, and that's why an upward arrow. It tries to find whichever is maxima. Here we can see there is no data above that small red curve, but the computer keeps going until it finds 0, 0 and stops right there. And then it also goes down. That is the descent. So we have to find the positive gradient and then the negative descent, so that we need to know exactly where a point falls. And to determine that, gradient descent has a specific algorithm. Like we calculate gradient, we did calculate the gradient through this simple slope formula, a mathematical slope formula, and update weights. The W is updating weights. So in our last video, we talked about the weights is in a way is related to the amount of connections or amount of data we can collect in the positive and negative. That's like a weight classification in a neural network. So right now we haven't hopped down to the neural network. We're just learning the theory part of how it works. So the mu right here is just it's a scalar quantity. It's just a like a multiplying factor right there. So the gradient, because you know that slope is going to be constant everywhere. That's a mathematically we know slope is going to be constant, but it's going to be differentiated by some value, a 0.3, 0.4, 0.5. So that is this new. This can be identified later on. And this is the TensorFlow command. Like I said, you'll be applying it right here. So importing TensorFlow TF. TF is also a variable. Weights is our variable. And then we put this random. We are randomly, because we chose a random point. So we are randomly initializing, asking you to take a point. And the command while true, tf.gradient tape. tf.gradient tape is the function. And then we find the loss, which is actually the loss function, and then we find the gradient, which is the slope, and then we determine the weights from that. So we know which is the accurate place for our region to be, whether the red region is good, or the green region is good, or the blue region is good. So that's like the heavyweight, or whatever you want to say. The region is plausible or good for our data, for our model to actually work. Back propagation. So when we come across this, we do hit a stone, we do hit a wall, a brick wall right here. Let's say around here, because the data keeps on descending. And what if the local max minima is somewhere we don't need it to be? We don't want it to be there. So there will be like a error where we have to find the accurate value and not neglect all these stuff. So that's the reason we need to find that determining factor is the back propagation, which we'll be learning right here. Computing gradients back propagation. So gradient is our slope. Let's say we are taking example of a very small neural network, X with weights 1 and 2. So we don't know which region is weights 1 and 2, but we know that it passes through this Z1 red, which is the hidden layer, which we talked about in last video as well. It passes on to the hidden layer. It gives the output y. Y is the output, and then the j of red. This is the loss calculation. We do, like I said, we find the loss after getting an inaccurate result. So that's how we train, right? We go back and get the data, and then we retrain it. We'll check whether it's accurate or not. Again, we go back and so that's the loss determination. How does change in weight and final loss, how it is affected actually. So again, this is a simple calculus problem. So let's take first two regions, these two regions first, these two regions, and so we do this what is this, a chain rule for the math and find the answer to it. And next step, we take these two regions, and then we do the exact same chain rule where it will be W1 d of jw, and then dou y dou by d w1, and that's it. So, and that way we can accurately get our back propagation value can be calculated that way. This is the theory formula of it. Later on, we can actually find the loss value, the final loss value. And moving on to learning rate. So learning rate itself defines us that it tells us that how fast you learn basically. Should the machine learn faster or slower or not learn at all? Or because it doesn't need to learn because everything is accurate data. You just give them positive data. Does the machine actually have to learn? Well, yes, it doesn't know all your data are accurate or positive. So it does need to learn. And not always the fastest learning speed is the best because it's not how it works. So initially, let's say we take the learning rate to be some point right here, which is 2. Let's say it's going to be 2 learning rate in the with respect to the loss function and your weight value. So right here, we take this point right here. We take this point right here. So you may not know its accurate learning rate because you have fixed your proper learning loss function and you have fixed your activation function. Your neural network is good. It's all okay. And you get the output and your loss is going on. But your learning rate, how fast it collects the input in order to give output, we never know that. And then like, let's say you keep on guessing like throughout this and it cannot be found. Okay, because here I drew the star because that's the place where this between these two is where actually the learning rate is most accurate for our model. But this is not the same for every single model, but our model is it has iterated that this is the best place. So we keep on learning, and this is a very lengthy process. Sometimes you take guess here, and then you go back here, take a guess, and then you take this value as a guess. So it's pretty complex, and you don't have to keep guessing a lot. You can directly fix a proper learning rate and train your model accordingly. You need not confuse yourself. So that's the reason. So trying a lot of different learning rates and what works just right, and that's the lengthy process. See, literally how many points here? I don't know. I can't even. It's probably like 50 or 60, and it keeps going because we need to attain this star, right? So imagine how many points. And even if you skip all these steps, you will be in a wrong position. You might be here or you might be here. So it's like that. So in order for that, we can do it adaptive way, adaptive learning. So like I said, every model doesn't have this sweet spot. Sometimes the sweet spot could be right here or it could be right here. We never know which is the sweet spot for a particular model. So how can we keep this same specific sweet spot? You have identified the sweet spot. We can't keep the same for your next project or next neural network. So we do adaptive learning. So what you do is you just write a basic algorithm for it. There is an algorithm for it. It will learn right here. So we'll go back to let's just talk more about adaptive learning. We have an algorithm for it. It will directly determine our gradient, and then it will determine the weight size, which is the region size, that small region size. It will determine it, and then it doesn't fix the learning rate yet. It will first go on to determine the biggest gradient and then the biggest weights, and then the lowest gradient and the lowest weights, and then the gradient descent, the loss, how much it is. It determines all these small values to compute the good learning rate for this. This is how it finds it. Mathematically finds every single bits, and then it puts it together. Puts it together in another function, in another formula to get the learning rate accurately. So gradient descent algorithms. So we did see the SGD. There are multiple gradient descent. We don't have to go in depth about it. SGD is this right here. This representation is the SGD because we did apply that algorithm to show you that image. We did apply that. So SGD is the very basic one. This is the command right here in the middle. Inference is the person who invented it. But let's just focus on these algorithms. And SGD directly, it gives you, or you don't need to worry about any of these. It directly gives you the learning rate to be set. It directly determines the weights and balances, and the back propagation problems are definitely reduced a lot. And then Adam, Adalta algorithm, these are pretty complex. We don't need to worry about them much, because even right now we are discussing about simple neural networks, so we can just stick with SGD, our loss determination and weight balances. Hope you guys learned a lot from these theory 2 parts videos which I have made in the past. Definitely follow my friends technical through our Codezilla community. They're making a lot of exciting stuff on different topics. If you guys love deep learning, make sure to hit like 100 likes. Let's see if we can video can get 100 likes, and I'll make an actual show you guys an actual working model of all this with these TensorFlow commands, and we can see it live how it actually works. There is a TensorFlow uh, this simulation website where we can definitely lot tweak around and have fun. You guys could go Google search right now, TensorFlow simulation, and there are a lot of algorithms, and it can show you how data are spread and everything. You can tweak around with your learning rates. And these are very interesting topics: learning rate determination and building an actual network. You can even I'll even show you all those stuff in the upcoming parts. And if you guys, let's see if this video gets 100 like, and encourage us to make it plausible, make it possible for the next video. So again, about me, let's just summarize a bit. Let's summarize. We did learn about loss functions, determining the gradient and descent, gradient being the slope and descent being going down and coming up, and back propagation, which is the problem. Again, from the when going this down, we'll get the negative values. Again, trying to learn is the there'll be a back propagation problem. That's the thing over right there. And setting learning rates. We learned that adaptive learning rates is the best, and then a few gradient descent algorithms. And then as about me, my LinkedIn profile is down in the description box. If you have any doubts, you can definitely reach me out. And then if you want to have learn more about these exciting topics, definitely follow Codezilla community. And these are all our socials. If you're active on Instagram, you can definitely come there. We do make exciting sessions every single month, or even thrice a week. We post videos. So definitely make sure to subscribe and like, guys. Thank you.